So, we are discussing the optical parametric amplifier we have in our lab, TOPAS C. What we have said so far is that we put in the beam, the pump beam, output of the part of the output of the regenerative amplifier we have using an all mirror telescope. And the reason why we need so many, why do we need so many mirrors? Let me ask you. Yes? One is path length. You might have to give a particular delay, because later on you have some other application, right. So, for that a part of the beam will go somewhere else. So, you need to give a path length. Secondly, you need at least 2 mirrors if you want to align a beam. So, as we are going to discuss, we already started in the last module, we will complete in this module. As we will discuss, alignment is very critical in things like this. So, generally life is much simpler if you try and make the alignment in such a way that at least in every stage the beam is horizontal. Okay. So, we do all our experiments on optical table, which in any case has this array of holes where you can put in screws and fix optics. The holes have a second purpose. They tell you which one is the vertical direction, which one is horizontal direction. So, if you want to make an instrument and you have to actually build something, the easiest way of trying to do it is that try and make your beams go along a line of holes, and to start with using a ruler, make sure that the height is the same. That way later on alignment becomes much easier, and if something goes wrong you can check easily. So, the steering mirror, at least 2 steering mirrors are required to ensure that the input is straight horizontally. Well, like this, it should not be like this, it should be like this, shouldn't be like this, it should be like this, right. Both these directions can be fixed easily if you have at least 2 steering mirrors. And this is what we have shown you. We said that you have light coming in from the region, and using beam splitter and different optics, we split it into 6 different paths. We have already discussed the first path, input beam, and we have started talking about the pump beam. Now, in this module what we will do is, we are going to talk about all the paths that are there inside our TOPAS. Okay. This is what we have presented already. Light comes in from the region, that is path 1, input pump beam. 80 to 90% of it is reflected towards M7, and we will see what happens after M7 towards the end of our discussion. The remaining part goes straight, and we said the next pieces of optics that this transmitted beam encounters are L1 and L2, 2 convex lenses. They are arranged in such a way that their focal points are coincident, and the L1 and L2 are chosen in such a way that the focal length of L1 is longer than the focal length of L2. So, that after the beam passes through this, you get once again a collimated beam, but a collimated beam of a narrower beam diameter, smaller beam diameter than the input beam. You require this because later on this beam has to go through several irises and all. A very broad beam would cause loss of energy and inefficient amplification, right. But let us see what is there before we draw the path, or maybe we will draw the path first. This is how it goes. Well, it goes further, but we stop it here because we want to discuss something, right. So, first of all, what we have said already is that L1 and L2 serve to decrease the beam diameter. Secondly, the other 2 things that are there right after this, and we are going trying to show you some isometric diagrams of these, not photographs. So, if you get to work on a TOPAS, it would be helpful if you first go through this presentation, then read the manual or read the manual along with this presentation, look at the isometric diagrams and go to TOPAS along with the manual and try to compare with the diagram to find out which optics is which. In order to run it intelligently, we must know what is what, otherwise it is baffling, and if you do it blindly, it is impossible to do anything with it. Okay? Right. So, what is DP1 and DP2? DP1 and DP2 are 2 well, I think quartz plates. The material is not mentioned in the manual, but 2 quartz plates that are set approximate Brewster angle. Approximate Brewster angle because you want to maintain the polarization. Now, I said approximately. So, actually they are a little different from Brewster angle. So, that polarization is not compromised, but what you can do is if you tilt these plates a little bit, any one or both together, then what happens is the light going through these plates depending on how much you tilt will go through more glass or less glass, right, and that would cause a change in delay. So, when you run TOPAS, this delay is called delay 2 in the software that runs TOPAS. So, if you change delay 2, what it means is that essentially you are tilting these plates. Why you have to change delay at all? Hold on, we will come back to it. Okay. And remember, we have still not answered that question, why is it okay to use lenses? Okay. Can you make a telescope using mirrors? You can, right, in principle you can. You just use concave mirrors of different focal lengths. It is just that you have to tilt them in such a way that the light goes out. Okay. Otherwise, if the output of these two mirrors keep on going, keep on oscillating between each other, it is of no use. But why do we use lenses? I mean, why is it okay to use lenses? We will see later, or why it is desirable to use lenses? We will see later on. But do not forget, the moment it goes through these plates, then also it is possible that you introduce some chirp. It is not an all reflective optics, TOPAS, okay, and that is fine. After that, if you produce this line, what do you get? What is the next thing? A1 is an aperture, okay, that is why it is drawn like this. You have this black little thing here, black little thing here, in the middle there is a hole, right. So, it is something like this, okay, section of that would look like A1. And then you have L3. What is L3? Another lens. What is the shape of the beam that goes into L3? Collimated beam. Now, when it goes to another lens, what will happen? It will get focused. Okay. So, why do we need to focus? We will see. Okay. But then after that, we have this BS2. BS2 is a beam splitter that transmits approximately 20% of the beam. Okay. Next piece of optics along this, think of this horizontal line, okay, that is a direction of propagation of the beam, as we are going to see shortly. After that, we have VF. What could VF be? Can we guess? In this context, what could F be? F could be, you can speak, in any case you will not be heard. So, if you give a wrong answer, it is okay. Yeah, F is, you are right actually, filter. F is filter and V is variable. VF is a variable filter because you want to play around with the intensity of the light that goes through. Why you have to play around? We will see later, remember. And the principle, remember, is too good is no good. You do not want to put in as much light as you can, that messes up things, we will see later. Okay. And then you have this M1, M2 and so on and so forth. Okay. So, let me draw the beam. BS2 we already said transmits about 20% of the white light of the WLG beam. This is your path number 3. What is path 3? WLG pump beam. That means with this beam that goes through, so how much of this, what would be the energy in this? You put in say 1 millijoule, okay. 80% of that, let us say, went on along path 2. In this direction, horizontal direction, 20%, 20% of 1 millijoule is how much? 200 microjoule, yeah. And then we are saying that this beam splitter transmits about 20%. So, 20% of 200 millijoule is how much? 200 microjoule, sorry. 20% of 200 microjoule is how much? Yeah? Yeah, 40 microjoule. And then you have this variable filter, so you can actually control. You can make it a little less than 40 microjoule as well. Not a little, you can make it 0 if you want. Okay? So, so that is a maximum, you do not want too much of light to go in. What is this beam going to do? This beam is going to generate white light. Okay. With the experience of doing pump probe spectroscopy, we know that if we use too much of energy to generate white light, or if we focus too hard, then the white light quality is not good, right. It is unstable, there is filamentation, many things happen. That is why, so that is the answer. That is why you do not want to use too much of pump, and I will show you a photograph of what happens when you use too much of pump once we are done discussing this. Okay. But this is your white light generating pump beam, WLG pump beam, goes through the aperture, L1, L3 focuses it. Now see, what is the role of L3? Why does it have to focus? Why does the beam have to be focused? Because your white light generation is going to take place in this WLG, you see, this is basically a sapphire plate. To generate white light there, it is not sufficient to send a collimated beam, you have to focus there. So, L3, the job of L3 is to focus the beam, pump beam for white light generation on the sapphire plate. Okay. Can you comment on the relative focal length of say L1, L2 we know already, right. L1 has to have a longer focal length than L2. Can you compare, can you comment on where L3 focal length will be? Should it be longer than L1? Should it be shorter than L2? Or should it be something in between? See, this is a cartoon, but this is roughly to scale. The way I drew the cartoon is that I started with that photograph and on that I have drawn the optics. So, lengths are more or less okay. So, what do you think? Just looking at what you see here, should the focal length of L3 be more than L1, less than L2 or something in between? Actually, it has to be more than L1, right, because what is the separation between L1 and L2? This much. So, depending on how much you want to shorten the beam, maximum focal length of L1 is something like this from here to here. But look at where L3 is and look at where WLG is. It is, this is the focal length of L3. So, L3 is actually a long focal length lens. It is better that way because you are generating white light. What happens? What is the difference between focusing using a lens of long focal length and a lens of short focal length? Finally, you focus and focal spot can be, well, your depending on what lambda is, it is the best possible focus you can get is lambda by 2. So, if you use a long focal length and if you use a short focal length, what is the difference? Let us say they are achromats. So, one answer is chromatic aberration might depend on the focal length, but let us say we are using achromats. Chromatic aberration does not even arise. So, for long focal length, the situation is something like this. Yeah, short focal length, the situation is something like this. This is called soft focusing. This is called hard focusing, because it is not just the point of focus, it is the volume of material through which the light is going through. If you do hard focusing, then you put in more energy for the same length, right. So, for white light generation or even second harmonic generation, sometimes soft focusing is better. You do not want to focus too hard. So, the solid angle is important. Okay. That is why you want to use L3 with long focal length, right. So, then what have we seen so far? Pump beam has been input, most of it has been sent along path 2, which is going to be used for the final amplification of signal. Small amount of it has been transmitted, and this, well, there is another beam splitter, do not forget, BS2. So far we have neglected the reflection of BS2. But if you look at the light that is transmitted through BS2, that light is used to generate white light. It is a pump for white light generation. Okay. And we have discussed this path 3 thoroughly so far. Okay. M1 and M2 are of course a pair of mirrors, in fact mounted on the same platform. And then there is an RP1. What is RP1? Let us see if you can guess. Yeah. So, it is a half wave plate. RP means rotate polarization. Half wave plate. Why do you need a half wave plate? Because you want to restore the polarization. the input polarization is horizontal. Okay. The input polarization for TOPAS is horizontal. For the next one, next stage you need vertical polarization. Okay. So, what this RP1 does is that it rotates the polarization to 90 degrees, and each of these steps is important. Suppose by mistake you take out RP1, or maybe you rotate RP1 so that the polarization is not turned by 90 degrees. What will happen? You will not get the next stage amplification. Okay. So, we need to know every component. All right. So, white light is generated. Okay. And what we have seen is L3 focuses into focuses this pump into the sapphire plate to get your this thing, to get your white light. As remember, we talked about delay 2. The problem is I have forgotten what the animation is, so I am saying things before I show it. Anyway, do you remember what is delay 2? Delay 2, we said that this dP1 and dP2, the two plates, you tilt them a little bit and bring in some delay. Will that change be large or small? Naturally, it is small. That is why it is called delay 2. So, we have talked about delay 2 first, not delay 1. What is delay 1? This M1 and M2 are actually mounted on a translation stage, and all these are motorized, controlled by the computer. So, you can move this M1, M2 forward and backward. So, that should remind you of the retroreflector that we use in femtosecond optical gating or pump probe for that matter, right. So, it can be moved forward or backward. So, that is coarse, right. So, that is delay 1. So, if you actually use TOPAS and if you try to control things by yourself, then you will see that you can play around with delay 1, you can play around with delay 2. Delay 1 is this M1, M2 retroreflector moving back and forth. Delay 2 is the plates tilting at some angle. So, delay 1 and 2 are your, so delay 1 is coarse delay, delay 2 is fine delay. It is important to know this because I mean only after you have played around with the coarse delay you want to touch fine delay, right. I ask you to measure the length of this room, what will you do? You will get a, I want you to measure it to the nearest millimeter, let us say, or even nearest micron. So, are you going to start using a vernier caliper from this end to that end of the room? No. First you will measure with a tape, right, and the last bit you will perhaps measure with vernier caliper. So, it is important to not forget that delay 1 is the primary delay, coarse delay, delay 2 is a secondary delay, fine delay. So, we should not, I mean, we want to play with delay 2 only when we are close. Of course, close to what? That we have not said yet, we will say. Okay. But delay 1 is the coarse delay that first has to be taken care of. All right. Now, what have we done so far? We have said that we have generated white light. Where have we generated white light? At WLG, which is a sapphire crystal, right. I have not shown the white light path in the next piece of animation, but okay, we will come back to that later. Right now I am not showing you white light, but you can guess where it will go. Where will white light go? It will go straight and it will hit L4. What is the need of L4? It has to collimate, right. Finally, you want collimated beams. With L3, you have focused the pump beam, right. So, the pump beam is going to diverge and the white light that you generate is also going to diverge. It is exactly the same as what you have in your pump probe setup. Okay. White light will also diverge. So, you have to capture it and make it collimated, that is the role of L4. We have certain things later on, we will come back to it. There is something more interesting later. And so, see, once again we are using a lens and we said it is okay to use lenses, maybe it is even desirable. We will see why it is okay. Okay. Next, let me show you the other path, path 4. What is path 4? PA1 pump beam. What is PA1? Power amplifier 1, or in other words, the pre-amplifier. So, of course, we have this BS2, we said 20% of the beam is transmitted, 80% naturally is reflected, right. That is the beam that we use for the first stage amplification of signal. So, where will it go? It will go up M3, maybe I will show you M3, L5, M4, DM, then goes through. Let us follow this path. Maybe I should have done it step by step. Anyway, so see, 80% of this beam that impinges upon BS2 is reflected to M3, and this is path 4, PA1 pump beam, goes straight, then goes through a lens L5. What is the role of L5? Again collimation. Do not forget that this is also a diverging beam, converging up to a point, then diverging, because you have used L3. So, L3 not only focuses the beam here, it is also going to focus the beam somewhere here. Yeah. So, it is going to focus both the arms, beams in both the arms. So, it is not enough to use a lens in the white light generation side. You also have to use a lens on the other side, which is the pump for the preamplifier. So, that is L5. Essentially, it collimates the beam. Next, the collimated beam goes and hits M4. From M4, it comes and hits DM1. What is DM1? Nothing to do with the initials of our celebrated colleague. DM here means dichroic mirror. Dichroic mirror. He is wondering who the celebrated colleague is. That is not so difficult to figure. Okay. Dichroic mirror. Why do you need a dichroic mirror here? Because see, white light will come from this side. Okay. That white light has to pass through. At the same time, you have to get this pump for the first stage amplification going in the same direction. That is why you use a dichroic mirror that will reflect pump. What is pump? 800 nanometer. Okay. And what is white light? It more or less ends by 800 nanometer. So, this dichroic mirror, is it going to be, dichroic mirror means essentially a filter, right? Can you tell me, will it be a long pass filter or a short pass filter? It is reflecting 800 nanometer and it is transmitting say 400 to 800 nanometer. Well, I have given you the answer. Yeah, it is a short pass filter. So, this dichroic mirror is essentially a short pass filter. All right. Okay. How far have we gone? So, this is taking so much of time. This is perhaps slide number 5 and we are into the second module and we are about to break again. Okay. How far have we gone here? On one side, we have generated white light. On the other side, we have generated pump that is going to selectively amplify one of the colors. Of course, when I say one of the colors, I mean modal color, femtosecond pulses, they are broad. One of the colors from the white light in the next stage. Okay. I would have preferred to get it done in this stage, in this module, but I do not want to rush. So, we will take a break, we will come back and finish this discussion in the next module.